Good morning, guys. This is a re-record. I tried to record by directly recording my screen and it was horrible. So we're going to look at the PDF version of what you guys actually have the ability to see online. So I apologize that this is coming up late, but again, when I looked at it, it was horrible. You can see all the objectives of the assignment, so you should be able to do these 4 things by the time that you are done. All of these things are pretty much review. There's a little tiny bit of new information that if you were not paying attention closely in class, you may have missed, but did come up in some of our discussions. Your key terms are all right here. Make sure you know what they are. They do appear on the assessment. Speaking of assessment, please stop doing the assessment before you've done the work. If you continue to do that, your grade is not going to move, and we really want your grade to be good. All right, so with that being said, the first thing that the STEMscopedia, which is basically like the textbook portion of the book, discusses is the atom, and that the atom was originally thought to be one indivisible item, but as they looked into it further, we figured out that they're made of electrons, which are on the outside. They're responsible for bonding. They're also responsible for protons and neutrons. Protons and neutrons are on the inside of the atom. That's where most of the weight comes from. Protons and neutrons together make up the mass of the atom, and they're found in what we call the nucleus. Protons are positive in charge, whereas electrons are negative in charge. And I think that's a baby. And protons and neutrons together make the differences that create isotopes, which is what they're talking about here, where you have protons in the middle of the atom, and then you have neutrons on it. Neutrons are also in the middle of the atom, and electrons float around the outside, and these are both forms of helium. If we look closely, the only difference between them is that one has one more proton than the other. Then we start getting into some of the different theories of atomic structure. One of the most popular one is Bohr. He thinks that electrons reside in energy levels or rings that move outside of the atom. The first ring holds 2, the second ring holds 8, the third ring holds 18, the fourth ring holds 32. Many of you learned that the third ring holds 8 in middle school. That's kind of like an oversimplification. So if you look at the periodic table, these 2 rows are your 8, these 2 sections. So this row here is your 2, then your 8. Okay, kind of hard to see there with the glare. Let's see if that didn't help. Okay, well, Father. Oh, it's the white paper. Got you. So the row with hydrogen and helium here, that row has 2, this row has 8. The next row has 8, so that's what they teach you in middle school, because they usually have you stop right about here or at calcium. But the truth of the matter is that third ring holds 18, 8 valence electrons, but then 10 other electrons that are not considered valence electrons. You can have up to 8 valence electrons. So then we get into valence electrons, and valence electrons are what is responsible for bonding. I will post a video from Tyler DeWitt if you haven't already seen it. That kind of goes over valence electrons, but in general, for the sake of our class, valence electrons, everything in the 1A column or the 1 column has 1 valence electron. Everything in the 2A, which is this orange, has 2 valence electrons. Then we're going to jump all the way over the yellow because they can change, and I'll explain why when we talk about metallic bonding. Over here we have 3, 4, 5, 6, 7, and 8 valence electrons. The top here one has a maximum of 2. Again, the numbers kind of tell you how many valence electrons there are. And I know that it's really hard to see these numbers. I'll make sure to have a real periodic table next time. But just make sure that you kind of know how to figure out the number of valence electrons, because that is key to figuring out many of our questions. Just trying to double check and make sure I don't have a periodic table hidden here, and I don't. Okay. Mendeleev is credited with figuring out the periodic table. Basically, he kind of organized things very similar to your periodic table project in order to figure out commonalities, and he even was able to predict a couple of elements down to their melting point, boiling point types of its density, and so he was credited with this. There actually were 2 or 3 people who were working on this all at the same time, but at that point in time, information traveling was difficult. It took a lot longer, whereas we submit something now, it's instantaneous, but it wasn't that way back then. We've already talked about how the periodic table is organized in groups. Groups go top to bottom, so this way, and periods that go this way. So everything that is red is in one group. Everything that is orange is in one group. It gets a little sketchy after that. These properties of these elements that are in groups repeat every 8 elements. So we sometimes call them families, and we refer to that as the periodic law. So then they start breaking up metals, nonmetals, and metalloids. It's kind of hard to see in my picture unless you're looking closely, but all of these are white. The ones that are touching the stair-step line are gray, and then everything else is a very dark charcoal gray. Everything that is a very dark charcoal gray is considered a metal. Everything over here is considered a nonmetal. These are metalloids. Metalloids act a certain way depending on what they're bonded with, but generally speaking, they have properties of both. So make sure you know these properties of metals and nonmetals that are here. We've already talked about valence electrons, and let's jump into noble gases are an important group because they have completed shells. So all the other elements are trying to be like them. They want to have either 2 or 8 valence electrons. We know that the atomic radius increases as we go down the periodic table because we're getting more and more rings. But going across the periodic table, it's shocking, the element gets smaller. These are the analogies I used about parents babysitting in the mall or walking in the mall. Basically, because you wind up with a larger effective nuclear charge. There's more elements, more protons in the nucleus. They're able to hold these electrons tighter, so it gets smaller going across. Ionic radius does the same thing as atomic radius does. They talk about ions here. Notice it depends on whether something is a metal or a non-metal, whether it gets bigger or smaller. Ionization energy is the amount of energy it takes to pull off an electron. And metals like to give away their electrons, so their ionization energy is low. But non-metals, they really, really like their electrons, and so they don't like to give them up. Again, we talked about ionic radius. It follows the same pattern as atomic radius for the same reason. Going down, we get more shells. Going across, we have a greater effective nuclear charge. Then we get into bonding. So there's 2 types of bonding. There's ionic bonding and there's covalent bonding. Ionic bonding, you have to create an ion by transferring electrons. These are, typically speaking, almost always a metal and a non-metal. So sodium is located over here, and it has a really low electronegativity compared to chlorine, which has a high electronegativity. And so what happens is, because chlorine likes electrons more, it has a high electronegativity, it's going to pull this electron off the sodium, and then they get stuck together because they're different charges. So in ionic bonding, it is a metal and a non-metal, 2 different sides of the periodic table. On the other hand, covalent bonding, co meaning together, covalent, together valence electrons. In this particular case, we're bonding things from the same side of the periodic table, specifically this itty bitty side in the corner. Things typically have similar electronegativity values, and so they share the electrons. There are some special situations, so typically they share a pair of electrons, 2, but they can also share 4, creating a double bond, or 3, creating a triple bond. Breaking these bonds releases a tremendous amount of energy. So most of our gasoline and our vegetable oil, our fats, have lots and lots of double bonds. Our explosives like TNT and dynamite, they have lots of triple bonds. Metallic bonds are when you have two metals together, like copper or steel, or gold, any metal, in order to hold itself together, especially when it's bonded with another metal, does metallic bonding, and that's where the electrons kind of float around freely, because they like to give their electrons away and they don't really want to hold them close, so they kind of share them. This is kind of like the potluck of electrons. Or so if we go back, ionic bonding is more like sodium has an extra pencil, and so it gives its pencil to chlorine, and because they now like each other, quote unquote, or are attracted to each other because of charge, they sit next to each other in class. Covalent bonding is this atom has the paper and this atom has the pencil, and so they share in order to complete the assignment. This one, metallic bonding, is a potluck. So someone brought the macaroni and cheese, someone brought the chicken, someone brought the collard greens, and we all sitting down and we're eating dinner together, and we all brought something to the table. But usually it's lots and lots of atoms and not just two, and they're all metals. And the electrons don't belong to anybody, so they're floating around freely. So pass me the macaroni and cheese, even though I'm on this other side. Then we get into the advanced topics of electron configuration. This is good to know for your final exam, though this goes a little bit more in depth than we went in class. The important thing in order to complete this week's assignments, though, you do not need any of the advanced topics, so you're good. All right, I think that is about it. That covers everything between this and Tyler DeWitt's video. So again, if you have any questions, I look forward to seeing you today at our conversation online. All right, thanks.